Okay, so for problem number 50, the first thing that you need to see, and this problem is very nice because it's actually telling you, define everything. Typically for a problem, if you're going to have something like this, it's going to go straight to C and say, what's the probability your total expenses exceed 400? But unless you do A and B, you will not get credit for C. So what does that look like? First off, when we're talking about defining the variables, you might not have this down from when we did it last class, but you need to talk about what each of the little pieces are. If you want to use D and C for cats and dogs, more power to you. I don't care. Just make sure you're using a capital letter. Make sure you're identifying your expected value and your standard deviation. But what A was asking you to do was to come up with an equation that represents this situation. And it's very important here that you have x1 plus x2 or x plus x and not 2x. Because it's not just taking the first dog and doubling its costs. They're two separate dogs. Now, when I ask you to describe a model, ignore this context. When I'm talking about describe a model, what does that include? Shape, center, spread. What is the general shape for this? The normal model. So when we talk about shape, center, spread for this satisfies everything. The shape is the normal model. I calculated my expected value and I got 320. So my center is $320. Spread is your standard deviation, but I can't do calculations with standard deviations. I've got to do it with the variances. So I took standard deviation squared, that's the variance of the first dog. Standard deviation squared, it's variance of the second dog. Variation squared for the cat. Get that answer. Square root for your standard deviation. You got to show that. Now, if you wanted to just do this work here, where we said expected value and standard deviation, you can do that. And then off to the side, say normal model. You kind of knock it all out that way. This is just kind of the short and sweet way of doing it. Every problem that you are going to be solving from here on out, you need to fit certain requirements. Describing what you're talking about, defining all of your variables, showing where all of your work came from. And then for the end, if I'm asking you to calculate a probability, what do you have to show me as part of your probability calculations? Z-score. So for this guy, my Z-score is the number I'm talking about minus the mean and over the standard deviation. So my Z-score is 1.45. I totally get that as of right now, you're still sitting there going, why do I need to do this? And the truth of the matter is when we're done with this year, we're going to have not just Z-scores, Z-scores, T-scores, chi-squared scores. And so it sounds like a lot of work. The formulas are almost identical in each of the cases. It's just telling me that if I use Z, I can use a normal distribution. T and chi, those are not normal distributions. So that's why we need to show this. It's telling me my test statistic. And then the way I did that in my calculator, I just did normal CDF. Actually, let me show you here. Normal CDF, lower, upper, mean, standard deviation. You can do this using Z-score, but if I put 1.45 here, what do I need to use for mean and standard deviation? 0 and 1. Good. Yep. Okay. Questions on that problem? What do I need to show? What am I talking about? Who am I? What language am I speaking? Yes, because you either need to have this statement here, or you need to draw a picture that represents the fact that my average is 320, my standard deviation is 55, and I'm going out about here with 400. So you can either write the P statement, probability statement, or you draw that picture. Okay? Yes? Yeah, I just did it in a different color because we had already done that for a previous problem. If you had done it before, you don't need to do it again, but you need to show it if it's the first time. Making the formula. And I just said C for cost. I mean, the only letter I wouldn't use a Z. Because Z is Z-score. Okay? Yes, ma'am. Right. Because A was just define the variables and express the cost you might have. Beautiful thing about this class, it carries. If you've done it in a different position, that's fine. As long as it's not, I'm asking you for something completely different here, and you didn't understand that. As long as that work is shown someplace, you're perfectly fine. Okay? Alrighty. So what I need y'all to do right now, we're going to take our quiz that we didn't take last class. So go ahead and clear your desks. Gentlemen, with this class, you guys don't seem to understand when I'm talking about like work that needs to be shown and how serious I am about that and how clear you need to be with your examples. But there's this really cute idea that they've done in all sorts of different ways. They do it in a lot of leadership training seminars and all that kind of stuff. But I thought this video would be a good opportunity for you to kind of figure out what I'm talking about. This class is about technical writing. It's not about writing a story or explaining it to somebody that you know or who you think has good understanding of what you're doing. It's about trying to explain it to somebody who's purposely trying to mess you up. So this is a great example of what I'm talking about.
Step 1. Get 2 pieces of bread out. Get a butter knife and get some cheese. Take 1 piece of bread, spread it around with the butter knife. No, Dad, wait, the peanut butter. It's doing what it says. It says take 1 piece of bread, spread it around with the butter knife. Hold on. Get some jelly, rub it on the other half of the bread. No, Dad, open the jar. This is the easy way. Put the breads together on top of each other. Take a big bite. I had to make it extremely specific. Oh, good. I'm sorry. Take 2 pieces of white bread out of the bag. Take the lid off the jar of peanut butter. Get a butter knife and stick it inside of the peanut butter. With the knife, scoop a bit of peanut butter out of the bag. It means a lot. Spread your
Look at her face.
There we go. Doing better than before, though. Open the jelly jar. Squeeze it onto the other piece of bread. No. Done. Open. Get 2 pieces of bread. Get some peanut butter. Take the peanut butter knife. Open the peanut butter. Put the knife in the PB. Get some jelly. Open the jelly. Squirt the jelly onto the bread. Take the butter knife with the peanut butter on it. Wipe it all over the peanut bread this morning. Take the butter knife, rub the jelly all over the bread. All over. Put the 2 pieces on top of each other. This is our bread. Take 2 pieces of white bread out of the bag. Take the lid off the jar of peanut butter. Get a butter knife and stick it inside inside of the peanut butter jar. With the knife, scoop some of the peanut butter out of the inside of the jar. Spread your scoop of peanut butter onto one of your pieces of bread with the knife. No! Squeeze some jelly onto the other piece of bread. Spread the jelly on the bread with the butter knife. Put your two pieces of bread, peanut butter and jelly sides together. Done. Get two pieces of bread. Get some peanut butter. Get some jelly in the peanut butter. Get the butter knife. Put the butter knife in the peanut butter. Take the butter knife out of the peanut butter.
This is the best.
Take one piece of bread and take the butter knife that has the peanut butter and spread it all over the top.
So which one is you and which one is me? You think you're the dad?
Put them on another piece of bread. Take the butter knife, rub it all over the top of the piece of bread.
I quit. You're not making any sense. You already ruined it on purpose. You know how it makes one.
I thought you guys would enjoy this. Okay, so I'll stop it there. But do you guys kind of have any idea what point I'm trying to make with you? No idea. The problem with this class is you guys are writing as if you're explaining it to yourself with the information that you know. And you're like, oh yeah, here's my work. This is what I did to get the answer. Yeah, that means nothing unless you follow the appropriate steps. Okay, this is not a joy of writing class or a tell me how you feel class. This is a technical class, okay, where we're doing technical writing. And you have to take every single precaution. You've got to think this person is an imbecile, knows no idea how to do this, or is going to purposefully misinterpret my instructions because I wasn't clear enough. And that's the way I want you to take into consideration what we're doing here today. Because today we're talking about probability models. And with this, we're starting into this idea of if you didn't tell me specifically what you had to, it didn't occur. I didn't tell you. The top of the bread is one of the sides that is white with a crust on the edges. I didn't tell you how much peanut butter. Take a tablespoon of peanut butter or two if you really like peanut butter and spread it from corner to corner of the white side of the bread. You have to be very clear with what we're doing here. We're getting into the point where we're talking about something called assumptions and conditions. And that means in order for us to take any steps, we have to first check to see if we even meet the requirements to go there. So what we're talking about in Chapter 16 is something called Bernoulli Trials. They're super straightforward, super simple, but if you didn't check it, it didn't happen. Bernoulli Trials only work primarily if you're in a very specific situation. And that means you have either a success or a failure, a yes or a no, a 1 or a 0. It is a binary choice. And when we talk about success and failure, we're not saying the success is the good thing, the failure is the bad thing. The success is meeting a condition. The failure is not meeting a condition. So you got to fit under that first and foremost. Then you have to be talking about a probability. And that probability has got to be the same every time you do it. And that kind of goes hand in hand with this last piece that says the trials are independent. The trials are independent means one is not going to affect the next one occurring. And we have all sorts of different ways that we look at that. The biggest one and the hardest one to kind of nail down is the idea of independent. Now, I can either be talking about something that I know is independent, like flipping a coin. That really should be independent. One coin flip should not affect the next one. Rolling a dice, independent. Other times, I need to think about what the situation is. If I'm selecting people to form a group, how did I select that? Was it random? It's got to be random. because that sample has to be representative. If it's not a representative group, why am I even doing this? Okay, there's also this issue about how big your sample is, because we're drawing without replacement over and over again. How does that affect? So let's just kind of look at two situations, and I want you to think, do either of those represent a Bernoulli trial? Now, it's just a yes or no answer, but when you're going through and doing it, you have to check. 1, 2, 3, each of those little pieces over there. What do you think? A. Yeah. And the justification behind that is, what would I consider a success? Not rolling 2 6s, but rolling a 6. Because it's either a 6 or it's not a 6. And then we do it multiple times. But each individual event is rolling a 6. Okay, so we know it's either a 6 or not a 6. Is the probability going to be constant? So what's the general probability for rolling a 6? 1 out of 6. Are each trial going to be independent? Yeah, what I get from the first roll or for one full trial is not going to affect what I get from any other trials. So I can say yes to that because we've met those 3 conditions. If I'm looking at B, what do you think? No, why not? There's more than one eye color. I'm not saying, do you have the best color of eyes in the world, which happens to be brown? I'm not, prejudiced or anything like that. Or not. If I had said something like that, do you have brown eyes? Yes or no? That's binary. That's success failure. But I'm asking you, what color of eyes do you have? That is not binary. So as long as you hit one of those no's, you keep on keeping on. Okay, so I hit a no. There are more than 2 possible outcomes. It's not a Bernoulli trial. Okay, these guys get a little bit more picky. Read through these, argue it out. Sometimes you can go multiple directions for your answer. Wow, you guys are arguing so quietly. It's almost as if no one's talking to anybody about this. I'm reading, Miss Augsburger. And just to be honest with you, I don't even agree with one of the answers that this question has. It's how you argue it. All right. Just curious, just give me a show of hands. How many of you say C is Bernoulli? How many of you say C is not Bernoulli? Personally, I fall in the not category. I have a different justification. They're saying it is. So I'm just trying to get you to see here, it's all about your thought process. Because it depends. If my thought process is built on something that's incorrect, but I got there the right way, then somebody else might say, okay, I understand your argument. I don't agree with it, but I understand your argument. And statistics is all built on this idea. Okay. All right, so we were talking about problem number C, or part C. And as we were going through this, we said that you can actually argue a couple of different ways. For those of you who said it was not Bernoulli, can somebody tell me why? Why you're claiming it's not Bernoulli? Nobody wants to fess up? Yeah. Well, it's not about what's good or bad. What's the condition that we're talking about here? Dangerous or safe? Recall or not recall? So it says, is the manufacturer likely to find any dangerous buttons? So that's what you're looking for that. Okay, so we do have the binary option here, success or failure. What's the main question here? Independence. Those of you who said yes, why did you say yes? That they are independent. Right, you're not going to have some creepy crawly doll on the shelf reaching over saying, my button's broken, ha ha ha, now your button's broken too. That would be really, really weird if we had jealous, angry dolls on our shelves that came alive at night and were like the nightmare version of Toy Story. You never know. Okay? So, that's a reasonable expectation. The dolls on the shelves should be independent of each other. But we have to think about this other thing, and that is, if I take one doll off the shelf, is that going to have anything to do with the next doll? The truth of the matter is, we don't really know how many dolls they had to start with. Okay, I don't know. So we would have to say we hope these dolls are what we call representative. We hope that these are an even distribution of everything else that we have going on. Okay? My argument was, I was thinking about the shipping. I was thinking about the manufacturer and the shipping, and I said, okay, it's probably going to be like a bad batch of dolls. And if they're just shipped out, you kind of get them in lots. So my mode of thinking was along those lines. And I said, you know what? If you're the group that got the bad lot, then no, they're not independent. Probability is not going to be the same, depending upon what lot you're in. And sometimes you see that happen with, what is it? Drugs. Okay, I was going more the spinach route. Yeah, a little bit different. Medicine. Huh? Kind of same thing. Where you might have an E. coli outbreak with a batch of spinach because, believe it or not, that usually happens when a cow poops in the field. And it's just not cleanly taken care of. Then that batch goes to certain locations. So they'll have recalls, but the recalls won't affect everybody because that batch didn't go everywhere. What they're saying here is they're saying, okay, these can be considered Bernoulli trials because we have only two possible outcomes, dangerous or not, good or bad, possessed or not, whatever it is you're talking about with these dolls. Okay? And then we have, as long as we have random, they're saying if I've got randomness, then independence should be okay. Because we should have a whole bunch of dolls, and I shouldn't worry about 37 dolls reducing how much is already out there. Yes, sir. Probability should stay the same. Okay? So it's kind of making that idea here. Now, if we have an infinite number of times that we can do this, then we don't need to worry about taking one out and having it affect what's left. But if I have a limited selection, there's going to be a certain point in time where my probabilities start changing because I'm not replacing them. That's what they're talking about here with the 10% rule. What about D? What do you think for D? No? Why? Right, because I only have, 19 people? No. Yeah, 19 people here. When I take one out, and I take another out, and I take another out. When I take 4 people out, I'm down from 19 to 15. That's a big percent jump. So this is bad because of that. We still have, we're talking about Democrat or not, but my probability is going to change as I go through the example. More specifically, the 10% condition. Let's kind of think about your senior class. How many people are there in the senior class? 750 something? So how big of a sample could I take without getting in trouble? 75. If it's 750 something, I can draw 75 people. If I want a sample of 100, I cannot do that because I'm going to have gotten so many people, it's going to affect the chances of the next one being selected. So when we're talking about independence, we're really looking at this. If it's like coin flips, rolling a die, picking a chip out of a hat or something like that, that's going to pretty much be independent. But if I'm talking about a limited supply, you need to make sure that it's less than 10%. And you want to make sure that each of those selections are independent from each other. Like there was randomness in there. And this idea of independence is going to be kind of like the ghost that haunts us for the rest of the year. And you have to check and you have to state these things. Otherwise, it didn't happen. So kind of thinking back to the video we saw with the build a peanut butter and jelly sandwich. How hard is that? It's an easy process. But you have to think carefully about all aspects. Now we're going to play a game, but we want to simulate it. We don't want to actually do it. All I want you guys to do is part A. Take out a piece of paper. Describe your simulation. Think very, very carefully here. Think back to Unit 3. How do we do a simulation? All right, so for part A, I want you to tell me what are things I need to include to run a simulation. A range of the numbers, okay? So that's your model. How are you going to model it? You need to do what? Repeats are okay. You need some statement about repeats. Random number generator. Go until. Single digit. All of these are really, really good. So let me show you what I've got. And I kind of highlighted here in a different color what I was talking about. First thing, you need to identify your component. So I'm going to let the numbers 1 through 6 represent the number on the die. Now, for that, because I'm specifically talking about the numbers 1 through 6, and all of those numbers are single-digit numbers, I don't need to worry about stating single-digit. If I were talking about the numbers 1 through 15, I would have to be careful with that. Make sure I'm talking about double-digit numbers. Okay? So you identify your component. Then how are you going to model that? So I'm going to use a random number generator, and I'm specifically going to do it on a calculator, because with a calculator, I can tell it, only give me the numbers from 1 through 6. So I don't have to talk about ignoring everything else. Okay? I'm going to generate random numbers. Repeats are okay. Then we're going to have our go until statement. For each trial, we're going to record the number of digits it takes to generate a 1. Or you can simply say, go until you get a 1. Then you need to talk about the response variable being the number of digits it took to get there. Okay? If I'm going to use my calculator, how am I going to do this? Did anybody remember how to do the random number generator on our calculator? Math? Probability? You do repeats, so we're going to do 5. Typically told you 1 through 6, I'm going to do that. And what I'm going to use is I'm going to use a number that's easy to count by. I don't have to how many. So just to make sure that you guys understand what I did, that was from math. We went to probability. Then we went from 5, which was rand int. And then I did from 1 to 6, and I picked a number that was easy to count by. Okay, and then to do these trials, I would simply say 1, 2, 3, 4, 5, 6. Hit it again. 1, 2, 3, 4, 5. And then just keep running through that. Oh, look, this one didn't have any. So there's 10, 20. It took 21 times to get through that. And you would keep going. So we're running out of time here. We'll stop there, which is actually a very good place to finish. No, because the run at least, because that was just the simulate, then the run at least came further.